Please let me know if you can see the complete slides or just the presentation mode.
The presentation mode.
Yeah,
yes. If you
now?
go, yes, perfect.
Okay.
Okay,
All
so
right.
I will introduce you first. So Tom Arya will, from the Ludwig Maximilian University from München, will talk about the assessment of speech production in cochlear implant users. So Thomas, please.
Thank you very much for the introduction, Julie. So yes, so my host institution during the development of the project in TAPAS was the Ludwig Maximilian University, and my supervisor was Professor Dr. Maria Schuster. So today I'm going to give you a very brief summary of the work that I did during my stay at TAPAS. So this is the outlook for the presentation. I'm going to then start with an overview of the project, then talk about a specific method that I implemented for automatic measurement of the speech quality of cochlear implant users. I'm going to show some of the experiments and results I got in my project, and then I will finish the presentation. So let me start by, most of you already know that within the TAPAS project, speech disorders are analyzed as the result of different clinical conditions. In my case, I focus on the people with limited hearing, and in particular with people with cochlear implants. So a cochlear implant is a device that allows to person with severe or profound hearing loss to get auditory perception. So it basically is a cochlear implant basically consists of a microphone and a sound processor to pick on the audio data, a receiver which is inside to transform this audio data into electrical impulses that are then sent to an electrode array, which is implanted inside the cochlea of the patient. These electrodes excitate different regions of the auditory nerves, and then these signals are picked by the brain and interprets them as sounds. So to give you an idea of how a person with a cochlear implant might hear sounds, we are going to listen to the sentence, "The sun is shining." So first, I'm going to play the recording for the normal recording.
The sun is shining.
I don't know if you hear that. I hope you did. And then I will play then a simulation of how a cochlear implant user might hear this kind of sound.
The sun is shining.
So if you notice the difference for the cochlear implant, the sound sounds like kind of muffled, like someone is talking through a wall. And if you keep listening to it like for a very long time, your auditory sound map might change. And then maybe this will influence also the speech production. So let's hear now a speech example from two German native speakers. One of them, first, we are going to listen to a person without any hearing or speech impairment saying the word zebra.
Zebra.
And now we are going to listen to a cochlear implant user.
Zebra.
So in this case, the cochlear implant kind of like mispronounced one of the phonemes. And these kind of problems were the ones that I addressed with machine learning methods during my project. So before I continue, I will then go over the things I did during my thesis. So one of them was to implement different machine learning methods to analyze different aspects of speech, such as the prosody, articulation, speech rates, and so on, to perform acoustic analysis and then to investigate about the influence of hearing loss in speech production. I also investigated about automatic assessment of speech quality, and in this case, the idea was to take a machine learning model for automatic annotation and then use the same model to assess the quality of the sounds that the person produce when speaking. And also, I supervise the development of two smartphone applications, one called Zeta, which was developed to evaluate speech and hearing capabilities of people with hearing loss. And the other one is Cochlear, which is actually going to be presented at the next InterSpeech. Is a children's version of Zeta. And the main feature is that the data collection is performed using a game-like interface. But for today, due to time, I'm going to focus only on the automatic assessment of speech quality using automatic annotation. So let me start with some motivation. Basically, hearing loss can happen at two stages of life. It can happen before speech and language development. So basically, when the children is born or before getting born, actually, they can also have some problems. And hearing loss can happen after speech and language development. So in the first case, um, the children must learn how to speak with the help of the cochlear implant. So this might be, let's say, more difficult for the ones that have to use two implants, because then all of the hear or all of the sounds they hear is only based on the perception or the based on the device. In the second case, the person already learned to talk, but if they spend too much time without proper auditory feedback, then they might need speech therapy to get like to the same, let's say, level as they were before hearing loss. So this is why in my project, the main idea was to propose and implement a method for the assessment of the quality of the sounds that the patients produce in order to, or with the aim that in the future this kind of technology might help in the speech therapy. And for this, then I take speech sequences, so speech recordings. I train an automatic phoneme recognition system, which is based in recurrent neural networks. And this network gives me a sequence of phoneme probabilities. In my work, I didn't did the phoneme recognition for specific sounds but for 18 different phoneme categories. For instance, stop sounds such as the P, T, K, B, D, G, labial sounds such as the P, V, M, and F, vowels, voice sounds, and so on. So for instance, in the case of vowels, as we see here in the figure, the blue regions shows the sequence of phoneme probabilities that the network gives for this specific recording. And it basically means or says that in these speech segments are the vowels. It doesn't matter which one specifically, but this is the class that represents the vowels. Now, again, I'm not going to go through the or show results about the 18 different phoneme categories. I'm going to focus mainly on the place of articulation categories. So the first one is the labial class or category, which means or refers to sounds that are produced by an obstruction of air coming from the lungs in the lips. So for instance, such as the P in pizza or the M in mother. Alveolar sounds such as the T in train or the S in speech, posalveolar sounds such as the sh sound in chip or vision, the Y sound palatal class for the Y sound as in yes and you, and velar sounds, which has the point of obstruction in the further back of the vocal tract, and this includes sounds such as the K in kid and the G in ghost. So let's see how I use these phoneme probabilities to measure speech quality. Here we are going to listen again to German native speakers saying the word Berg. So let's hear first for the first speaker.
Berg,
And in the figure, we can see that the phoneme the network give us this sequence of phonemes for the labial and velar sounds, which are the only ones that are present in this example. For now, we are going to forget about the vowels, and now we are going to listen to the second speaker.
Bert,
If you could perceive that the second speaker actually doesn't pronounce the G, actually at the end sounds kind of like a T. And what happened now is that the phoneme recognizer doesn't recognize the velar sound in this case, and also give us some posterior probability that seems like it's relatively lower compared to the first speaker. So how do we measure the quality of the production? What I did was to take the maximum value of these detected sounds and use this as the feature to represent the quality of the sound produced. So the higher the probability, the better. So 1 is the maximum value that you can get, and 0 is the minimum. And for the second speaker, then we take again the maximum. For the velar sound, we don't have any velar sound, so the probability is 0. And for the labial, we can see that it's relatively low compared with respect to the healthy control. Okay, so now I'm going to show you some partial results that I got using this methodology. And for this, I consider speech recordings from German native speakers. All of them were asked to read 97 words, which contains the different phonemes, the different German phonemes in different positions within the words. So I consider a group of controls, people without any hearing or speech problem. In this case, I have 20 participants. Also 20 participants, cochlear implant users that lost their hearing after speech and language developments or postlinguals. And also 20 cochlear implant users that lost their hearing before a speech and language acquisition or the prelingual groups. So here we see the results for the assessment or measurement of the speech quality. At the bottom, we can see the result for the 5 different classes that I explained before, and some examples for you to remember what I'm evaluating in that case. Remember, the higher the value, the better. The blue bars represent the control group. The dark gray, the postlingual, so people that lost hearing after speech development, and the white parts, the prelingual cochlear implant users. So one of the interesting patterns that we can see here is that for the velar, palatal, and postalveolar sounds, there is the most, let's say, difference between the controls and the 2 groups of cochlear implant users. And this is quite interesting because this represents the sounds or the classes that belongs to non-visible phonemes. So for instance, in the case of the velar, for the C in cat, you don't actually see how the articulators are put together inside the vocal tract. So this is what I mean for non-visual phonemes. And so it is interesting because most or some of them has to learn how to speak or go to speech therapy, learning by looking at the people making the sounds. Another pattern is that for the postalveolar class, so the sounds such as in should, we can see the highest difference not only between controls, but also between the 2 groups of cochlear implant users. And let's see why this might be the case. So in this case, we have a control on the left saying the word spine, and a prelingual cochlear implant user saying the same word on the right. The red line represents the phoneme posterior probability for the postalveolar sound. And then what we can see is that for the control, it's evident that the network is able to recognize the sound being produced. But let's hear if we can perceive these kind of differences. So here we are going to hear the example for a control.
Spinne.
Spinne, and now for the prelingual.
Spinne.
So I don't know about you, maybe because I'm not a German native speaker, but for me, it's hard to tell whether they are mispronouncing the word. And I don't actually see a problem. But if we look at the spectrograms, we can see that the energy distribution between the control and the prelingual is quite different. And there are many studies that has linked this to the spectral resolution of the implant. So if you listen to this kind of sound with a different weight through the implant, then the hypothesis is that the person shifts their productions towards the sounds they hear, and thus they produce different sounds. This is not proven with this. I mean, we need more data to actually have a very conclusive result, but it goes towards the main hypothesis, and this is actually quite interesting that we can detect this with this kind of methodologies. So to summarize, then I presented here a methodology that I use for the automatic measurement of speech quality of people with cochlear implants. Some of the limitations or the work that is has to be done from now, or the future work, is that I didn't have the chance to consider longitudinal data, so to analyze whether this kind of methodology could be used to evaluate the person over the time. And also, one thing that I missed was to get data with the smartphone applications and to maybe evaluate this speech technology for smartphone data. About the smartphone apps, I'm actually going to talk about more tomorrow for the 10 minutes talk. But as of now, this is where I finish my work, and this is what it comes next, like to keep going with the project. So that was everything from me. Thank you very much for listening. And if you have any question, please don't hesitate to ask me.
Thank you, Thomas. Any questions first here in the room? Yes, there's one off there.
Hey, Thomas. Thank you very much for the nice presentation. I noticed that you compare three groups of speakers like control, postlingual, and prelingual. And I also noticed that their age, well, at least the mean is pretty, well, they're a bit different. And normally people can imagine that the hearing ability will be impacted by the age. So I'm wondering, aside from this postlingual, prelingual, do you also analyze whether there's any age impact on the results?
Yeah.
Sorry.
No,
Or have you do any control of their hearing ability before before start the experiments? Thank you.
Yeah, thank you for your question. Yes, there is a huge difference in age, and for this kind of system, I actually do in my thesis have a chapter on the impact of age in this kind of methodologies, and yes, there is one, but in this case, it is not the case, mainly because I'm going to show you something. I did the same experiments for people, yes, with two groups of controls and cochlear implants. All of them were in the same range of age, and it was also, I mean, it's match between the two groups. And what we got was that we have the same patterns in this case for the same classes. So in this case, we assume that the age is not that much of a problem in this case. Actually, the prelingual group, which was the one with the lowest posterior probability, is the youngest one. And according to the results I got in my thesis for the age-dependent stuff, the youngest people has the higher posterior probability. So this is why, in this case, I don't think that the factor influencing the results is the age, but it's actually the, let's say, effect or the limited auditory feedback and the influence on the speech production. I don't know if that answers your question.
The microphone was off. Sorry, Thomas, thank you. I'm very satisfied with your answer.
Hi, hi, Thomas. Thank you for the presentation. I was just wondering, so the way you like get this automatic measurement of speech quality is by training this BLSTM over this 18 class, I think.
Yes.
How does it compare with using an other, like the posterior of an ACERS or even an acoustic model, and then group the different like posterior different classes by group? Do you know? Do you have any idea how it compares?
You mean using the classical automatic speech recognizer to do the same task?
Yeah, but you just like group the different like phoneme like depending on the class.
Oh, yeah. Unfortunately I didn't have like I didn't do these experiments, so I could not tell you how much different they are. Actually, I try at the beginning doing this like this way, but it was a lot more harder than I thought, I will say. So this was kind of like easier because I in this case I have to skip let's say the language model and so on.
Yeah.
And yeah, I mean, I don't have the direct comparison with a classical automatic speech recognizer, but that will be definitely something nice. Something that I did do was to use a force alignment and then look at the posterior probability. I mean, there is a huge difference because since the network doesn't have, I mean, it can detect another phoneme that it doesn't actually, or is not actually being produced in the recording. And this might be either an error or something that can be beneficial. For instance, we tried this also in children with cleft lip and palate, so nasalization. And what we saw is that when they produce a sentence that don't have any nasal sound, the posterior for the nasal appears there. And I mean, it kind of makes sense in that case. So yeah, that's what I did. So we tried with the force alignment. With the force alignment, you can see which sounds were actually produced and how well they produced. Yeah, according to the phoneme recognizer. But with the network alone, you can get posterior probabilities of sounds that might be there, probably because of mispronunciation or some other, I don't know, clinical or factor which is affecting the voice of the person.
Okay, thank you.
Thank you. Other questions? Are there any questions online?
I see one actually. I guess it was only for me. I will read it. It says, since the deep neural network recognizers look at a large window of frames, they can learn to use the context of a phone to predict the posterior of the central frame. How do you prevent that the posterior is base influenced by the context instead of the central part, which you want to evaluate? Yeah, this is actually hard to control. The only thing or the thing I did to let's say reduce this kind of error was to use a small oh, I forgot chief step size. Sorry, a step size and a small speech frame. I tried with different length for the two of them, and at the end I got kind of like the similar results if I use 1 millisecond, 20 milliseconds window and 1 millisecond step size, and 10 milliseconds step size and a 20 milliseconds window. So it was similar. Of course, it's more precise with the 1 millisecond window, but this is like the only method I could think of to minimize this kind of error, like to play with the temporal resolution.
Okay. Thank you, Thomas. I think we all, at least we here, we need urgently a coffee break. So we will move the coffee break to now. And then after the coffee break, we will continue with the presentation of Abdesalim. So please all enjoy, and we will restart, let's say about 20 past 11, no, 25 past 11. Yes, okay. So please enjoy.